Around 2015, it was a large jump in our results because we start to mount cameras from our grant, so the number jumps. And in 2016, we cross the number 100,000 of detections per year, which was very happy for us that we managed to collect such a huge amount of data. But next year the number drops, so this is the data for the last year, and I will show how why it happens, what caused this drop in the data. So you can see that the number of calculated orbits for 2017 is more than 14,000, and this better quality orbits is 10,000 for the 2017. It's about 3,000 less number than the previous year. And here you can see the coverage of our network. The dense parts are the regions where we observe with our more sensitive systems, and the rest part is the regions which we can observe from the farther distances with not so sensitive systems of our cameras. And most of the data we have from the region of Central and East Poland, but we can also observe some meteors above Slovakia. And this is without the numbers, but with a graph showing the number of detections. As you can see, the number of the last year detections is almost similar to 2015. And a similar graph for number of calculated orbits. And here are all the numbers. Counting everything from 2011, we are nearly 400,000 of detections in this period, which I summary here. And our cameras divided to 3 groups. We use very low-cost cameras to cover a huge region of Poland. This costs only a few euros, so it is possible to mount a lot of them in our system. But we have also the more sensitive cameras, which based on minitron cameras, and now it's 14 or more. Even more digital cameras. We changed these low-cost cameras with new ones, digital cameras, which have similar sensitivity like these low-cost cameras, but have a lot better resolution, so we can get much better results of calculations. We have also testing nearly all sky systems, and I hope in next year we will show some more interesting summary for this system. Here you can see the top 10 cameras in our network. The best one observe more than 4,000 meteors per year, and this 10 best cameras observe in total 37,000 of events. These are months and total of the year. Data from our cameras are sent to 2 servers to have redundant data in two sites, and this way we make the safe storing the data, not to lose anything if something will happen. This is the distribution of data through the air for every night. So you can see that the data comes mainly from the main showers, for example, for quadrantids, Perseids, Geminids, and the red line comes from 2016, so the best year in our statistics, and the blue line is from the last year, 2017. As you can see, there is no Perseids here. We have not such luck to observe the maximum of Perseids last year. You can see here, and this is the gap, because in Poland, exactly at the maximum last year, there was no weather, and we have no results here. But we have good weather for Geminids, so the most the biggest peak for per night we observe for Geminids, not for Perseids, what is unusual in our data set. But because Perseids are active much longer than Geminids, and for Geminids we have only one night when the good weather was in Poland. So the Perseids are still on the top list of the most observed showers by the Polish Fiber Network in the last year. And this is cumulative distribution of data through the air, which helps us to see which part of the year we observe more the data than other. It is easier to look at this graph than the single night, because we have only the many peaks, not the statistic we can see from that graph. So you can see here that for the first half of the year, we collect only 20% of the data, and mostly statistically for many years, the number of data grows during the Perseids, and the last year also is more we record more meteors than in the first half of the year. And when we compare results from many years, we can see that the best year, this orange graph, orange line, rapidly growing in here, which is September. So in the September last year, something different happened than the last year, and this way we, how much? Huh? 6 minutes. Okay. So something happens here. We check this on the detection of the clouds in Poland. There's meteor network which gives the information how many clouds are for specific days. So I use this to compare the weather in 2016 and 17. As you can see, for 2016 we had very good weather in September here, but in the last year we missed that. This is the main reason why we have this differences. In 2017, our network looks almost the same like X60. As you can see here, these two lines goes almost exactly the same in these two years, up to this point when this lines goes completely different, and that's why, because the weather here was very bad. We hope this year will be much better, because there is completely strange weather in Europe in this year. In Poland, the good weather starts in April, and it goes up to date. So this is we expect a large number of detections this year. So, thank you.
Questions?
Do you only use the small sensor cameras, or have you already installed large sensor cameras like DSLRs or so?
No. For now, for today, nowadays, we use only these video cameras, so the small chips. The biggest chip for now we use is 1/2. This size. But earlier we observed using DSLRs also, but long exposures.
So you mentioned switching from analog to digital. You saw an improvement obviously in resolution, but do you also see an improvement in photometry because you got that 12-bit depth instead of 8?
For now, software use only 8 bits, but we know that these cameras could use 12 bits, but for now it's too slow to use everything. So in the future, when we upgrade the software, probably we can change to 12 bit, and the quality of the estimation of brightness will be better.
Any other questions?
Just what is your limiting magnitude?
It depends on the version. For analog cameras, these cheap ones, it's about 2. For these digital cameras, it's similar, about 2 or 1.5, something like this. And for these micron cameras, it also depends which lenses, because we use lenses 6 millimeters, 9 millimeters, 12 millimeters, so this depends. But it's better, it's about 4 or something like this.
Speaker again. So next up, Felix will tell us how single antenna meteorite impacts.
Okay, good afternoon. So this presentation is on behalf of myself and 2 collaborators. This is the first family contribution consisting of Steve Lettenfields. Unfortunately, they are not here all because there's also school duties nowadays. Well, I got the honor to present our results. So let me first start with a map of the Netherlands, which is a meteorite map. This shows what kind of interests all our meteor people have. So you see cameras, you see meteorites plotted. And in the Netherlands, there's kind of a tradition, a little bit still of visual observing. So a lot of video work going on, but we have also all sky cameras. And that's the reason that there are also meteorites plotted. For the best informed, this already outdated this map, because there are 5 meteorites here plotted, and we have in the meantime 6. And I like to go a little bit into the detail of the fireball work. I have here printed 2 all-sky cameras that we use, that are both my own, based on DSLRs and good fisheye lenses. And with these we of course capture fireballs. This is a special one which I want to share with you, because this fireball appeared exactly at the time of the previous IMC and kept me awake for a whole night, and Vincent as well. And this was the picture that was taken by a camera in Dwingelo, pretty far away from the fireball, but still a very nice trail, I think. Well, so if you have a fireball, then there starts all kinds of work, and we have a number of people in the Netherlands who like to analyze this. One of them is Marco Langbroek, where you see a plot of this analysis of a big fireball which we called the Gaasterland. I will give a little bit more details later on. Calculated where it could have dropped because we thought that there can be something on our Dutch grounds. And another example is a little area below Boenderlo, which was also photographed by several cameras. And with the help of Pavel, we were able to compute the impact point and also the dropping area where we could look at. Now, then of course, a new phenomena starts. Meteor observers also starts to look for meteorites. And here you see some sphere photographs. And on the right side you see a plot of that area of the Netherlands with GPS trackers, so we start to search very minutely the fields looking for a meteorite. We learned that it's a lot of work, it's very time consuming, and apart from lots of volunteers, you have to do a lot of more work. You have to ask permission to be on the field, and you have also to prepare the whole community in that area such that they know what's going on. So we made little printouts that we brought to the houses in the area, and we tried also to involve local people with help and even manpower. And here you see an example of that. Moreover, we also organized in one case a local exhibition in a village house where we explained about meteorites, and in the hope that people came with suspected stones so that we could analyze them. We brought then lots of real meteorites to show what we're looking for. And here you see Dushan pointing to an empty spot because where we hoped to put what we wanted to collect, but no success. And that is the main point of my story. So we had in the last 3 years 3 search campaigns and still empty hands. So what do we do wrong? We hear always nice fireballs and meteorite recoveries, and in the Netherlands we have no success. Do we put less time in it, or do we something really wrong? Now, some teaching about the Netherlands. Here you see a map of the Netherlands. This is from a world atlas, and if it is green, you know it is flat. Well, the Netherlands is extremely flat. There are no mountains. The left part of the Netherlands is even below sea level. At the right side, you see the type of ground that we have, and that goes from sand particles to very fine clay particles and all kinds of ground types in between. And we have loam in the very south and peat, which is really fluffy. And well, if you want to translate that into what you can expect now, if you want to go to the Netherlands and have a nice holiday there, this is sand ground. Here we have loam, which is in the very south, with thicker, there are smaller particles, but more dense. You have clay, there's absolutely no firm to work at, and even worse is peat. And that is the last fireball which we had was last year, January, the Broek in Waterland. That fell in such an area. Now you can barely stand on it, you sink away. And likely meteorites do as well. Why did we find it is your question. I come to that in a minute. So let's have a look at the Dutch history. Here are the 6 Dutch meteorites which we have, the 8. And I tried to find in historical documents where they dropped on. Now most is sand, one penetrating clay layer, more clay, sand, and the 2 most recent ones, so in our era, it was very easy, they fell through a roof. So no success at all. Now what is the real reason why we found the other ones? Well, because at that time there were many workers on the land and they just were standing next to it. So they saw, in fact, the meteorite falling and just had to grab it from the ground. Now, very interesting. I also tried to see, well, what did they find? They found little dips in the ground up to half a meter, 75 centimeters. But that was our real question. We were looking over the field, and where do we have to look at? A hole or a stone on the grass or whatever. We had no real clue. So that popped up a new thought in my head. Can we simulate an impact? And that was very exciting also for my kids. So we started to work a bit on that. The first thing I looked at is at EMO and at the AMS. Is there something about the velocity, how they impact? Well, it is. I calculated a little bit myself, and I know that fireballs, they decelerate, and at some point they do not decelerate much more. They lost all their initial energy. Then the gravity starts to affect, but you have also friction in the atmosphere, so there comes some equilibrium. And then you can calculate what kinds of velocities you get. And I find them as a function of mass that you are in the order between 50 and 120 meters per second or so. So 1/3 of the sound speed. The bigger ones, that is 10 kilo or more, I think the chances are rare that we find them. So let's focus on the smaller ones. So is there a way to do it? I had to think, hey, split guns. Each could buy in the past. You put a potato in it, and there's air pressure, you shoot the thing out of that. I knew that you have amateurs who build themselves these things, and they are already a bit more powerful. So I thought, is this a way to do that? So this is the drawing table, and the conclusion was, yes it is. You can construct from some pipes a big pressure tank is in the middle, a cannon pipe, and then you put pressure in it and you can eject something. And the big technical problem is, how do you get that pressure instantly on your fake meteorite? And that you do with a little or big piston, which is drawn here. You pump it full with air or something else. You create some under pressure here, and then the piston moves suddenly to the right, and then all the air comes immediately on the meteorite, and you can have huge accelerations. 200 gram meteorite, diameter of 7 centimeter, we assumed, 10 bar pressure, the length of the cannon in the order of 3 meters, and you can create 370 kilo thrust on the meteorite, accelerations of 20,000 meters per second squared, and exit velocities of 185 meters per second. Ah, sounds good, eh? I thought at least. Here you have a little table, depending on mass. These are the velocities. There's 2 bar and there's 10 bar. So we have a certain range, and this would work. That is at least what we thought. So time to work in the weekend. Here I'm making the piston, which is 170 millimeter across, and this is how it looked. Do not go to your do-it-yourself store. This stuff you cannot buy there, because the wall thickness of these tubes is 10 till 16 millimeter. This is all pipe which you use for pressure, water pipes, and all this kind of thing, up to 16 bar. So safety first. Here you see it then in our backyard. Test facility we do not really have. And then you think, this is getting dangerous. No, it's not, because there are people who do much better than me. And now I expect a question, is this all legal? Well, it is, at least in the Netherlands, because the Weapon Act states it should be flammable or explosive. And if it is compressed air, there's nothing wrong. So, and now we have to start a movie. We will try to do it together, because then I can also show you the sound. Are you ready? Yeah? Go. Oh, that's the wrong movie. That's the wrong movie. Boom. Laten we beamen. Has de beamer staan? Okay, then it works.
Hold the microphone to the beamer. To the loudspeaker. Should I do it? Try.
This one?
Yeah.
Where's the loudspeaker?
They don't all.
This one.
Okay. So maybe once more. You have to look at over there. And
At least it's cuts roses.
yeah, so here we look now. This was really the first shot. So we are also ourselves surprised what happened, and we were highly surprised because it was indeed some damage. And it is only 20% of the test, so the design pressure. We find that there is wall. We can go to the next slide.
What about the neighbor's car?
No, the wall is still intact, but there's a wooden plate of 2 centimeters thick, and that little hole that you see. You can now go to the next slide. So, tennis ball was 65 grams. This is what it makes, and this is what it was after the test. So it's a very small meteorite. So, other movie. Also sound. So this is from 65 gram to 50 to half a kilo. So here we had a half a liter water bottle, which we did. And here you start already to see the back movement of the gun and the whole thing there. This. Okay, well, I hope so. You can enjoy later on. So this is what left over of the water bottle. Please do not do this at home. We were also a bit scared to see what happened. We have it pretty much under control. It's a serious business. Now I have another movie which is also important to show. So, yeah? Go. This is the same shot, the second shot, only we use the iPhone in high-speed mode. It's 240 frames per second, and you see how now it comes out. And that we needed, of course, to see what kind of speed we got out. Now, here's the frame by frame. You see the plume coming out over there. You see it also with the tennis ball over there. And then you can calculate what kind of speeds you want. In this case, 72 meters per second, and our model is 44. That are these speeds. Design speed was 68, and there what was 188. I was wondering how is it possible that this is lower, but then I realized that we just put the tennis ball in, and we did not really close it, so there was some pressure leakage, I think. So overall, I think this was a success. The gun works. And the next step is to put not tennis balls anymore in, but real meteorites. So this is a plastic ball, which in the meantime we have transformed these stones and concrete into representative meteorites. So that is the next step. And then, this is my last slide. Part 2 is to come next year, because what we want to do is this gun. We will put it in several areas in the Netherlands, we travel around, and we shoot it into ground, sand, swamp, and etc. We like to do that in several seasons, winter, autumn, summer, and then monitor once per 2 months how the damage in the ground varies. Because I think myself, if we have to look into a swampy area that after a very short time all the evidence of a meteorite is already left out. So this is in fact my last slide, and I hope to come.
Questions?
How do you want to mount the cannon? I mean, the meteorite will be down probably perpendicular, so
Yeah.
the cannon has to fly 100 meters? Or
No, the idea is not to shoot up.
Okay.
It will cause problems and gets out of control. So we built a steel scaffolding construction and it shoots vertical down.
Okay.
Nice experiment. Just to mention that your impact speed are, let's say, about twice overestimated.
They are lower.
Yeah.
Okay. That makes it
You
easier.
need not such big gun.
And then to bigger stones.
I think Bartel's concerned that he's not going to be the only one in the CIA to watch this with cameras. Okay. Thank you once again. So coming up, we're going to have Esther and Teresa talking to us about NEMO, which stands for the Near Real-Time Monitoring System.
Hi again. Yeah, we just wanted to give you a quick update. Oh yeah, there's a question. Yeah, just the status of the project. Yeah, the very important one is we finally settled on a logo. Yeah. Yeah, just a quick overview of the project itself. Can you hear me? Is this working? Yeah, the emphasis is that we want to find bright fireballs, ideally all over the world. We are not only interested in meteors. And the goal of this project is to have a nice model for the fluxes of meteoroids in a bigger size range than what we usually get for meteor research. Yeah. The current situation is like if there was a bright fireball, something that was seen by a lot of people, and of course by a lot of different networks. All these different, they all have different information, which are of course interesting, but are not bundled together. So with NEMO, we'd like to combine them so that we have a place where we can find the information a bit easier. If we have a fireball that is brighter than -10 magnitudes, we want to put these informations, all that we've gathered, into the fireball information system from the near Earth, the Space Situational Awareness Center in Frascati. They want to know about objects that regularly impact the Earth's atmosphere, but are too small for the near Earth asteroid surveys. But still cause bright fireballs that cause a lot of public attention, so people ask about it, but they don't have the information on hand. Yeah, and so to close the gap between the small meteoroids that are very well looked after with the meteor camera systems and stuff like that. Yeah, just to have the The data sources for this are what we are working on right now, for example, the CTBTO, which is infrasound data from the Comprehensive Nuclear Test Ban Treaty Organization. Yeah, the publicly available data from US government sensors, the Janice can answer that already. Yeah, reentry predictions, of course, to find out if it really was a fireball or maybe just something man-made that came back. Yeah, very interesting data source, of course, the social media, which are very fast, but not always that accurate. Yeah, of course, the meteor networks, which are very good information, very scientific ones. Yeah. Our objective is that for Europe, we'd like to see everything that is larger than 10 centimeters. One nice example is this Netherlands fireball, which we wrote a report about for EMONet. Yeah, and of course there's a Coupon network that we are very excited about because they are looking for fireballs. We work with Jeremy on this one person. Yeah, we want to work with him on it. So far we haven't done that much yet, but now we are. Yeah, on a global scale, we'd like to see everything that's larger than 1 meter. Yeah, for this, social media, as I mentioned before, is a very interesting source because they're very fast. Yeah, then the US government satellite data, where Jensen's already told you what the limitations are. Our main concern is that they are not that fast, so we have to wait a while to get information. Yeah, the infrasound is a nice source for global information, which is not constricted to only nighttime. We get the information from the International Monitoring System. We've been to Vienna, where they store these data and analyze them in the beginning of the year. I was there for a couple of months too. And there we use infrasound signals and use a period to find the energy of a fireball stuff. Yeah, a bit hard to analyze, I have to admit. Yeah, and Esther tells you about the NEMO events.
Thanks. Now we want to show you how NEMO works, so we will just do this for one example. So everything starts with a Twitter alert. Or in most cases it starts this way. So this is one tweet, and it was just the first one we received for our event. So we know, oh, there was something, there was a bright fireball, oh, it was in Russia, and in some cases, even with our first tweet we received from our alert system, we even know when it was. So in most cases we only know the day, but sometimes also we know the time, and here it's also the time. Then the next tweet give us a video in some cases, then we know, okay, it really was a fireball, since sometimes there are only airplanes or strange things in the clouds or so, and people are saying, what is it, UFO, meteorite, and our alert system finds it. So then we receive some videos about it. And yes, our alert system finds more and more Twitter alerts. And for this case, we also received our alert for infrasound data. So at the first step, we knew that it was detected by 4 infrasound stations. So we knew that we will be able to compute an energy for this fireball. So when we know there's infrasound data, or if it's a really huge event, then we ask if there is infrasound data available. In this case, there is information on 10 stations all around the world. Here they are, and here what the event was. So it's the computation result from the 10 infrasound stations from the CTBTO. And then we have analyzed the data and computed a source energy of our object. So we concluded with a source energy of 2.4 kiloton TNT, and NASA published a value of 2.8 kiloton TNT, so we think this works, but still there's a lot of things we have to learn about this, and there's just a huge error interval in this infrasound data. So we concluded for our fireball that the entering object would have had a size of about 4 meters in diameter. So the next step of our NEMO event are the Google alerts. In most cases they are a little bit slower than the Twitter alerts. And they give us more information about our event. If it was a really huge fireball event, then there is additional information. For example, here that it was detected with radar. So I'm not sure if you have seen it. Can we start it again? There it is. Okay, so this was found by our Google alert system that there was a detection here. Okay, and then we receive more Google alerts, for example, that there were meteorites found related to this fireball. But still, for this example, we have seen again that people still are faster than just Google alert system or anything else. So we received an email by Galina about half a day before our Google alert system found that there were meteorites found. And at this point, I also want to mention that there's a poster by Anna with more information about this Russian daytime fireball. So they found 3 meteorites related to this fireball, and the smallest one had a diameter of about 3 centimeters. So at the next part, we compare with the results from EMO. Sometimes they also are the fastest source of information, that there are first a lot of reports on the EMO webpage, and then we know there was something, and then we are looking for more information. But for this case, we started writing our first report on the EMO webpage on this fireball and added all information we have from our NEMO system. So only a small overview for our NEMO events. We are in test operational mode since about 1 year, and in total we have about 135 events in our database. So we first thought that it should be growing, the number of NEMO events, with our time and when our system gets better and better. But the larger problem is not to receive the alerts, but to receive less spam. So we still have to do a lot of work on this, but we think in most cases, if something happened, we know about it already. Yeah, and just, we still have a bias through the population in the United States and also here in Europe. You cannot see it so good, but there you have more reports since we have the email, the AMS data is very fast, and in Africa there's not so much information. Here you see also the Botswana event where we have received a lot of alerts of our 2080 LA asteroid. Okay, to give a short outlook, we want to stable the NEMO monitoring of our social media. So this all have to work more automatically and has to take less time for us. Then we are really planning to start with our free-form flux determination to get a little bit more science with all the data we have. And we have to find a reliable infrasound energy determination and the semi-automation. So in the moment, if there was an event, we have to ask for data and then we analyze it by hand. It takes a lot of time and still there's a lot of uncertainties. And yes, we want to analyze and to assess as much data as available from all data sources that are possible and to combine it to get the maximum amount of scientific information about one event. Yeah, thank you for your attention.
Do we have any questions?
Why is there such a big variation from month to month in the number?
That's a good question.
Yeah, that's really a good question. It's like we sometimes have 2 weeks and nearly no event, but sometimes there are about, I'm not sure, on Monday there were 2 events at the same time, one in Australia and one in the US, so it's really, really different. So, and also we only have the really huge events in our database, so not all events that are small. We have this brighter than -10 magnitude, but it's not so easy to start with. If we don't know how bright a fireball was and we only have this Twitter alerts, you have no idea from the sightings what it is, really. Yeah, so here we hope for more scientific information. Yeah.
Do you have a hashtag?
We have to.
For specific hashtags or something like that? Because maybe for language it can be a problem for research. So if we know that you have a hashtag, if we see a tweet in other language, maybe we can just tag you there.
Yeah, that's a good thing about Twitter. Everybody wants to be found, so they're actually using the English language hashtags. And also our program actually finds the ones when that's really the 2 words that you're using, if they're in a different language, usually finds it as well.
Yeah, but still there are some different databases, not in all countries they are using Twitter or Instagram or anything like this. So this is something we were planning to do when this is work stable.
And a comment on this, there is other works that show this with all historical data. We talked about it.
Okay, that's cool, thanks.
Do you know what's the detection limit of CTV here in terms of energy? Size of the block?
It depends a lot on the direction. Oh, sorry. It depends a lot on various factors. How close was it to the station? Can we just detect it by one station? If we know that something happens, we can just look at one station, but usually they only find something that was detected by more, so they can actually say it was an event. But if we look manually in the data, we can of course bring the detection limit down. And it depends of course on the conditions as well, and on the conditions of the station that was close by. They differ a lot on various sites.
So what's the smallest you've seen so far that for which you determine the size?
You have like one here.
So it's about the same limit as the US government sensors.
Exactly, a little bit lower maybe.
Any other questions?
Yeah.
And how big is limit to classify some event as NEMO event?
Yeah, it's, we have to have scientific data to actually know the brightness, which is our proposed limit for that. But so far we don't have scientific data for everything, so it's a bit tricky actually to. That's true.
Your limit is if that event is on the net or on Twitter, there is a NEMO event.
Yeah, we don't have any set parameters yet. We like, for example, how much attention it calls it or something.
Okay.
Oh, sorry. We don't have a set of parameters clearly defined yet.
Yeah. Okay.
Are you guys working with media so that if there is a viral event, they can kind of come have you as a portal to all of our data? Would that be a good way of them getting correct, more scientifically correct data on virals?
I think this database is supposed to be for ESA, so they can talk to the reports.
Cool. Let's thank speakers again. We'll be taking a 40-minute coffee break / close to sessions, and we have to invite you all to come back at 4.
Just a short announcement. There are still a few people who need to see me because they still have to pay the registration fee, or sometimes a small balance for a t-shirt they ordered later. So please do that I can close that part of my job. For the rest, of course, you can still apply for membership, and you know, if you pay here, you get a €5 reduction. And there are also some publications that we have brought with me, which you find on the table. They cost between 10 and 20 euros. If you are interested, just ask.
Voltamos depois do coffee break, pessoal.